All right, so here we are in exploit development. We're coming to the end of the semester. There's only 3 more classes. So this one is Chapter 14, Protection Mechanisms. And I made the last 2 quizzes extra credit if you want to do them because, don't have a lot of time to absorb the material, but I thought it's worth covering because it's interesting stuff from the book. So let's talk about protection mechanisms. And I think maybe like that would be good. All right, so the non-executable stack, we've talked about. The NX protection prevents you from running code you've injected on the stack. And the general principle of Windows and all modern operating systems, every memory segment should be either writable or executable, but never both. And a lot of stack data protection to stop you exploiting buffer overflows like we've been doing. And then heap protections and structured exception handler protections we'll talk about. So there are general protection mechanisms which just try to reduce the probability of an exploit being successful without completely patching it. And those are good. You can often apply those even to old code that hasn't been recompiled. Running old code on a box, the operating system can add some of these, although the ones we're going to talk about today do require recompiling, I think most of them. So if you write a simple program in C and it's got a variable and array, a character array, and then another variable, early versions of the C compiler would just load these on the stack. They're local variables in this function, so they'll go on the stack, and it would just put them on the stack in the order of them being declared. So var1 first, then buffer, then var2. That's one way to do it. And then the saved base pointer would be here, and the saved return address here at the end of the stack frame. So if you're able to overflow the buffer, you'd be able to change this variable, and if you overflow it more, you'd be able to change the return address and gain control of the EIP. All right, so one thing you can do is have a non-executable stack, and that means even if you can manipulate the EIP, you won't be able to run code that you've injected on the stack. You'd have to find a way to put your code somewhere else. And this is now the default on almost every modern operating system. You can still overwrite the return address, and that's just hit by a read operation, so it would still take effect and redirect the execution somewhere, but it won't be able to run code that you injected on the stack, which is the way most early stack buffer overflows worked. So there's a series of techniques, return-oriented programming, where you use the fact that you control the EIP to execute shellcode that is not in a non-executable section. So you can put shellcode in the data section if you find a way to do that, and then use the corrupted return value to jump to it. So that's return to data, or you can return to libc. Now you can just jump directly to any C library function like printf or scanf or many others, or system. And if you do that, when you jump into a function, it expects the parameters to be on the stack. So since you control the stack with your overflow, you could fill the stack with appropriate parameters and then put the address of a function, so you could make a function call with parameters. So that's a good idea. Of course, you can't inject a null byte if you're doing a string injection, because that would terminate your string. So there are some limitations, but you can do that. You can return to string copy. Now, string copy will copy an array of bytes to another location under your control. So you could put your shellcode on the stack where it won't run, but it sits there as data, then return to string copy and copy the shellcode to another location, because you control the destination address, and then jump to your destination address, which you control. So that's one way to do it. And here's what it would look like. Before your overflow, it's here. After your overflow, you'd have a string copy here, you'd have your shellcode up here in this slave section junk, and then your destination memory to copy it to, and the destination address to execute it, and the source address, which would point up here to some section you control in the stack, and it would copy this somewhere else and then run it somewhere else. Then there's return to gets. Gets reads data from the keyboard. So you'd be able to define the address where you want it to go, and it would then read from standard input if you have control of standard input. Then you'd feed in a series of characters which would then be copied to this other memory address, and then you can jump to that. And here's return to gets. You just put gets here, the destination address, and then the destination address you want to jump to, which would be equal to this or related to it. So then you read a bunch of characters from input, which are copied by gets to this location, and then jump to it. Then ret to code is the standard way, and we've used this, in fact, in that Vuln server project where we just used Mona to find a trampoline code in another module, which was not a Windows system module. We jumped to that code, which was put there. It was in a DIL file that came with the application. So this is the generic idea. This is the point. All return-oriented programming relies on the same principle. You do not add code to the app exactly. You just reuse some of the code that's already there to accomplish a different goal. And that's the game. You jump through real code that does something, or just fragments of code that you paste together, like a ransom note you make by cutting letters out of the newspaper. And that's called chained ret to code, where you would just do a whole series of calls. So you jump to just the end of little routines, so you get a couple of operations like a push or something, and then a return, and then another push and a return, and you piece together all these little fragments of code to add up to what you want. Now, you do need to move the stack pointer, and you're going to need to fix the stack pointer after each return, which would require pop, 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 return, because the stack pointer is going to be, when you do the return from a function, it will try to move to the next stack frame, and you're going to have to move it back to the stack frame you're working on. Or you could return into functions using other calling conventions, which fix the stack on return. And there's return to syscall. Syscall, of course, is the jump to kernel mode. That's really how everything happens. So you could do it right to that. That's int80 on Linux and syscall on Windows. So you'd have to first pop all the needed arguments into registers, because you have to load the registers and then go to syscall. It's easier on Windows, though, because the syscall arguments are on the stack and you directly control the stack. So this is about as easy as return to libc on Windows. And then return to text. This is where you jump into the text section of the binary you're exploiting. And that's where the binary's code lives. So that would be nice if you can find it. And that stuff is always guaranteed to be executable, because that's where the program runs. All right, and you could also jump to the procedure linkage table, which we've corrupted in some of our exploits. The procedure linkage table contains pointers to the C library functions that are actually called by the program. So it's one way to go where you can find your way to the C library programs. That's an option. Or you can jump to the dynamic linker resolver, where you can get to any C function, even a C function that is not used by that program. All right, so the non-executable stack, as we've been discussing, means you cannot directly run code on the stack, but that doesn't mean you can't exploit the box. You can still put addresses on the stack pointing to executable code, which will then be executed. All right, and so here's something you can see of these stack defenses, and this is from ED303. Let me bring up the project. I'll demonstrate the whole thing later, but a little bit of it is relevant to what we were just talking about here. Stuff towards the end of 303. Yeah, that's what I want. I want this figure here. Okay, so let me bring up my Windows machine. I made a new Windows machine and it was working better. We'll see if it's going to work for me well enough today. So if I do a directory and see what I've got here, I've got a program called mem1 and one called mem0. And mem1 is to 102,000 bytes. This is compiled with standard protections, and mem0 is compiled without the standard protections, without address space layout randomization, and without stack cookies. And what this program does, if I look at the contents, mem1.cpp, okay. All right, what this program does is it just defines some variables, a pointer to point to the stack, and various. So here it just prints, here's an address in the text section, in the data section, in the heap and the stack. It just defines variables in those locations so I can see them. And then it prints out the contents of the stack. That's what you see here. It's just pointing to the pointer. The pointer is here. And it's just going to show you a series of 9 pointers on the stack. So let's run that mem0 or mem1. And so that would be here. This is the one with normal defenses. Okay. So you see text, data, heap, and stack addresses. And here's the stack with a series of variables on it. And if I just do this a few times, I can make a sort of animated display by running this program a few times. So notice the first thing is 181.033, and it doesn't change. It's always the same. Look at the second one, 199.HC0, that's always the same. But the next two, the heap and the stack, where my arrow is, those change. Every time I run it, they change. 6 and 4, 8 and 6, and so on. So those are the two things that are randomized as a defense. The heap and the stack are randomly relocated in memory to make it hard for you to jump to addresses in there. And if you look at the stack itself, the 1 stays fixed. The second number, the item 0 stays fixed. Item 1 varies. The next 2, 3 are fixed. 5 and 6 are changing. So the ones that are changing are 1, 5, and 6. All the rest are the same every time. And that's explained here in the project. So these yellow circled things are the ones that are changing. The stack and the heap move because of address-based layout randomization. Word 1 points to a location on the stack. So it moves with the stack. See, if this is 9EF, this is also 9EF pointing to a location on the stack. And these two, 5 and 6, this is the stack cookie, which is the defense added here, this random number, which changes every time you run the program. And the point is, if you have a stack buffer overflow, and word 7 is the frame pointer, is the return pointer. So if you try to overwrite the return pointer here, the stack cookie will prevent that, because as soon as you change the stack cookie, it will detect that and not run. And this is the saved EBP. So that's the base pointer, so it moves along with the stack. So you can see the layout here, and it's sort of a handy way to see what's going on. And if you turn off the defenses by compiling it with gs- to get rid of the stack cookie and linking it with dynamic base no to get rid of ASLR, then you get this program called mem0. And if I run that one, if I run it a few times, you can see that all of the top 4 items, all the memory segments, never move. 4, 4, 5, 1, it's always the same. So there's no randomization. Oh, excuse me, the heap is moving, but nothing else is moving. And in the stack, almost everything is constant. In fact, everything that matters right up to 5 is unfixed. The reason 6, 7, and 8 move is because they refer to a different stack frame. So those really have nothing to do with this program. But all the ones above it never change at all. What's the difference between a stack cookie and ASLR? An ASLR randomizes the location of memory segments. The stack cookie is this value here. Well, it's not in this program, and it's a value here, which is just a random number, which it writes when you first enter the function, and then when you leave the function, it makes sure it is not changed. So they operate in a completely different way, but they both protect you from buffer overflow exploits. All right. That's a very important question. That's the point here. All right. So that's the demo. All right. Let's take a look at a Kahoot. See if I can get this nonsense. Okay. Sure. It's a good question. It gets right to the heart of what we're talking about. This is chapter 14A, right here. Okay. All right. By the way, I had a student that couldn't do ED319. I fixed that, so just try it again. Anyway, the server was unreachable because of a DNS problem, which I fixed. All right, maybe that's all we're going to get. All right, so which one uses shellcode placed on the heap? Oh, I see. Yeah, that's return to data. All right. Sort of a funny word, but that's what they say. All right. All right. What attack can use DIL code that the target executable did not load? Yeah, it's this one, ret to DIL resolve. I don't remember seeing that in the slides. I must have skipped over it, but that's it, of course. All right. All right, which one puts shellcode on the stack but executes it in a different memory segment? That's a string copy. Copies the data from the stack to a different memory segment. All right. Which attack reads stell code from standard input? Yeah, that's return to gets. All right. Fair enough. All right. Now, there were a couple of those I didn't like much. Let me go look at the slides back here a bit. Let's find that DIL resolve one for one thing. There it is. Okay. ELF's dynamic linker resolver by using library functions that are not used. Okay. It is using different libraries, but I kind of wonder, I don't think that would apply to Windows. I think my Kahoot question is kind of wrong because it made it sound like it was on Windows, and this is Linux. I really don't think you can do that on Windows. And the other one was return to data, which went to the heap, which I didn't expect. Okay, you have to put it in the data section, and one way is to use buffered I/O, which would put data on the heap. Okay. Is the heap in the data section? I guess it might be. Yeah, okay. Well, I understand that a little more, although I'm not entirely quite sure I understand the addressing the heap. But I guess it has to be in the data section. I don't know where else it would be. Okay. Anyway, all right, so on we go. So write or execute. This is the way all modern memory segments are. So it's either writable but not executable, or non-writable and executable. So the text section that you execute cannot be changed, and the areas that you write in, like the stack, cannot be executed. That's the idea. And the idea is injected code won't run, because if you can write there, then you won't be able to run. That's the idea. So an early implementation of this was PAX. It turned out to not be popular, though. I guess it slowed down performance too much. The NX bit is what you've all been using on Windows for a long time, also called data execution prevention. It's been around for a long time, and Microsoft has made it so the client versions of Windows, like Windows 10, only apply this protection to the essential services, but not to all the programs you might download and run. On the server, it applies it to everything. And you can change that, but by default, client machines, they figure people want to download and run a lot of random software, and servers, you probably only want to run like trusted commercial products that are high quality. That's the general idea. So change ret to code will still work, as we've said. We've used it, where even if you do not inject any executable code anywhere, nothing but just a table of addresses, that's enough. You can just paste together your code from the other addresses. That's return to code. There may be a memory segment somewhere that allows write plus execute. And then you can use change ret to code, write to disk, and then execute that. One thing that people used to do a lot back in the days of Windows Vista was use a Windows library function to change the permissions to write plus execute. And that was a big deal back in Windows Server 2008. I haven't been able to do it in later versions. There's another defense that's blocked at least my attempts to do that, though. So that project is no longer present in your projects. All right, turning it off. Yeah, there's a library call. You can do that, but it involves injecting null bytes. And like I say, I had trouble doing this on modern versions of Windows. I think there are even more defenses that I don't thoroughly understand preventing it. Changing a specific memory region. The virtual protect, that's what I tried. Mona will do this. Mona will give you change addresses that will perform a virtual protect operation. But it didn't seem to work when I tried it in Server 2012. All right, then you can just do it sequentially. First you make the region writable, and then you change it to executable. That's another way to do it. And you can also use virtual alloc, another thing I tried that did not work on modern versions of Windows, to create a new region memory, write plus execute. All right, and then there's stack data protection. So canaries were the first one. Something called stack guard was the early version. The modern version now included in GCC is called ProPolice, or stack smashing protector. And this is what I was showing you. In the old days, you would put the canary right here, right before the return address. So if you overflow from, say, this array of bytes here, you can overwrite the base pointer and the variables, but you can't hit the return address without overwriting the canary, and it will detect that. So that's all right. But that was stack guard. ProPolice moved this to protect the base pointer also. So then you have to choose what value to put there. Now, in the early days, they would put a null canary there, just nulls, figuring that you won't be able to inject null bytes, but it was always the same. Then they made a terminator canary, which is everything that might terminate a string. Null bytes, carriage return, line feed, or one of these is carriage return, one of them is line feed, I can't remember which one, and FF is end of form. Can I explain what canaries are? All right. Well, a canary comes from the idea that you have a caged canary on a stick that you stick ahead of you in a coal mine to see if there's poison in the air, because the canary will pass out, and then you'll know the air is no good. It all serves that purpose. So the point of a canary is now you add an extra byte here, which just sits there. When you first enter the function, it puts a number there, and when you're trying to return and use the return address, before it does that, it checks to make sure this canary has not been altered. That's the idea. So the canary is your clue that somebody has been corrupting the memory. That's the idea. And it's working pretty well. But the early versions weren't so good because they tried these predictable canaries. That was the idea. And now mostly everybody uses a random canary. Sure, good, okay. All right. So this is another thing that is enforced to try to protect you is the ideal stack layout. Remember I mentioned how a compiler in the early days, the simplest thing would just put the variables on the stack in the order the developer declared them. But it turns out it might be better to just move all the buffers to the end of the stack frame, so that if you do overflow the buffer, there won't be anything other than another string variable past it, which is less likely to be harmful. So that's the plan. So it copies, all right, so it rearranges your orders. So it will put your arguments here, and it would put the variables up here and put the buffer right at the end. So that if you overflow the buffer, you're just going to hit the canary. So you can't hit anything else and change other parameters. That's called the ideal stack layout. All right. However, both of these modern defenses are not on all the time. Although there is a switch, you can compile it with these defenses on all the time if you want. But by default, it only puts those defenses on functions that look vulnerable. And the rules to determine if it's vulnerable are if a function contains buffers. Well, anyway, I think the rule, I'm not sure it's in my slides here, but I think the rule is you have to have a buffer and it has to be bigger than like 5 members or something like that. Yes, canaries are used by default by all modern compilers, I think. Unless you turn them off, they're being implemented in at least some of the functions, although not all the functions. The functions that appear to have a string variable that could be overwritten. So here's some vulnerabilities. Even if you have a canary, you can still overflow from one string buffer into another string buffer, and that might give you some ability to exploit the program. You can't rearrange structure members. If you define C structures, they cannot rearrange them. They have to have exactly the order of the layout, so it cannot change that to the ideal layout. And if you have a variable number of arguments, then again you can't put that in an ideal layout. So the defense is not always effective. All right, and so if you dynamically allocate buffers, they're always on top of the stack frame. And like I say, there may be something valuable to you that you can hit by overflowing with a small injection, not big enough to hit the return pointer, but it still hits a few other variables, and you might be able to find something there you can use. Another thing that's implemented is ASCII armored address space. This is where you load all shared libraries in low memory, starting with null bytes. And then you won't be able to inject any of these addresses, but null bytes is the idea. However, this is better on big endian architecture because, as we did in some of the projects, if you have little endian architecture, you can inject one null byte. It terminates your string, but if you're writing an address, this byte here is the last one you inject. So you'd be able to inject one address into here, even though it has a null byte. So if you want to execute this Linux command and you want to execute system, you can make a call to system by making the last injected byte null, even if system is an address beginning with 0. So here's a diagram of that, defeating ASCII armored address space. So here you are. So you put in your padding, you put in the frame pointer, you put in the payload, which is readable text, and then you call system, and you see that you're injecting the address here, and that jumps you back to system, which is the null bytes, is the last byte of the string, and it's interpreted as the most significant byte because you're little endian. All right. The main executable, however, is not moved to the armored address space, so you could just use code in there. So like all these defenses, it's not perfect. Let's take a look at another Kahoot. However, like antivirus, even though these defenses aren't perfect, they did end particular attacks being run at those times, It's kind of all you ever get. You get to stop some attacks, and then the bad guys write some more attacks. All right, I think that's it. All right, so what defense places shared code in low memory? All right, that's ASCII armored address space. All right, what defense causes code to stop when it hits an up? All right, that's a non-executable. That would create an error message when you try to execute any instruction, including an op. And I see Cersei said you got an exposure notification. You know, I've never heard of those actually helping anybody. From what I can understand, they're like false positives mostly. The one on your phone anyway. Anyway. So what defense uses carriage return and end of file characters? All right, that's the Terminator Canary. I also kind of wonder if those exposure notifications mean anything, because now we don't seem to be bothering with COVID protections. A bunch of people are wandering around infected without tests, without getting reported. So I wonder whether it means anything. Anyway. All right, what defense protects the return value but not the stack frame pointer? Which is EBP, the base pointer. That was stack guard, the early one. Good. All right. All right. Okay. So, address space layout randomization. This is where you randomly locate code in memory, as we saw, and you could see not everything was randomized. 2 areas moved, 2 areas didn't. All right, this means performance has affected. It has to keep a record of where the segment is somewhere now and refer everything to it. And in 32-bit OSs, it is more expensive because there aren't enough registers available to, how random is this random? Yes, well, that's the point of that project. You'll test it later. In fact, in early versions of Windows, like Windows Server 2008 or 2003, it was not very random at all. I think 2008 is where it came out. And it turned out that it was only like 14 bits of randomness. They improved it in later versions. In fact, I think we're getting there. Anyway, so ways to defeat it. You can copy the code to a location under your control, or you can trick the application into telling you an address. So you find out where you are. You might find addresses in the register or on the stack. Linuxgate is a table of pointers for system calls, and sometimes it's at a fixed location, so it is a useful area to attack that's always in a place you can find it. And as we said, insufficient randomization. If there's 8 bits of entropy, that means you have only 256 random values, so one simple way to make your exploit work would be to just run it a few hundred times until you get lucky. And Heap Cookies had only 8 bits of randomization in Windows XP. In Windows Server in 2003, the cookie's still 8 bits, but there are other defenses. All right. Anyway, also, if segments move together, then you only have to have one guest to protect them all, so that's another weakness. All right. If you can escalate privileges and access this memory map. On Linux machines, it's just in process PID maps is the memory map. So if you can read that memory location, you can read the addresses. And of course, brute forcing a 16-bit value is not that impossible, 65,000 choices. So if you can actually run your exploit 65,000 times, you can get lucky. A 24-bit value would require you to have 16 million runs, which might be possible sometimes. All right. So if you have a format string exploit, we've seen that before. Format string exploits reveal addresses on the stack, and you can find useful things there. That would give you addresses that would point to where things are. There are IPC calls that leak memory addresses. And if you have multi-threaded applications, the address space has to be the same for every thread. So if you find an exploit in any thread, it gives you enough information to locate the memory segments of all the others. Fork is the way Unix typically creates new processes. But the fork does not re-randomize the memory layout. So there may be a relationship between the old process and the new process. All right. And then there's heap protection. We talked about this before. If you have chunks on the heap and you delete one, the forward and return pointers are updated. And if there was an overflow where you were able to change these values, you end up controlling a write operation where you control the address and the value written to an arbitrary location, and you can use that to take over the box. So if you want to avoid that, one thing it does is safe unlink, where before it frees a chunk, it tries to make sure that the forward and backward pointers are okay. So it tries going from the thing you're about to delete to the previous chunk and then back, and to the next chunk and get back. So that would verify that these pointers are okay and that those pointers are okay before you free it. So that's nice. And that's implemented in glib and Windows for a long time, almost 20 years now. However, not all heap operations are protected by it. And there's this thing called the malloc maleficarium, which is full of complicated, confusing ways to get around that. I looked at it a bit trying to write projects, and I decided it was too confusing to bother with. But you can read it if you like and see complicated exploits that find heap overflows. Heap exploits on Windows, unsafe unlinking. What you can do is overwrite the back and forward pointers carefully so the check will still pass. But the pointer still does something good. You could make it so that this forward pointer actually points somewhere wrong, but override it so it can still find its way back. You might be able to make it past this test and still be corrupted. All right. And there's other exploits. There's a thing called the look-aside list that records free chunks, I think to prevent heap fragmentation. And that's a place you can write to. There aren't any security checks there. But it's not used in modern versions of Windows. Instead, there's a newer thing called a low fragmentation heap. There are also heap cookies, 8-bit random cookies in each heap chunk's header, so that if a chunk is freed but the check failed, it will not do anything. So this is the equivalent of stack cookies, where it would put a cookie in here to detect if you've been overflowing the data into the next heap. So it sounds good, but it's only an 8-bit value, so it wouldn't be too hard to brute force. All right, but in Vista and later, all modern versions of Windows, it's now 8 random bytes. And that's used to validate each chunk's header, and there are other integrity checks. And all this, I think, comes from Microsoft's Blue Hat program. Microsoft used to say hackers are evil and we'll have nothing to do with them. But around 15 years ago, they gave up and they started running CTFs and bug bounties. And one of the early ones is the Blue Hat program. They invite selected people to come in, and then they invite you to hack Windows, and if you get in, they'll pay you a bunch of money, and then you get to write the defense that would stop that. And their defenses started getting very good. The heap defenses are really quite impressive these days. They have a lot of tests of the heap to make sure it hasn't been corrupted before using it. So Windows 8 added even more protections, all these things, heap handle protection and LFH non-determinism, whatever that is, lots of things. These come from hackers who would hack into Windows, and then they would help Microsoft write the defenses, at least some of them, I think a lot of them. And you see they now have a lot of cookies for all these different features to make sure they can detect overflows. Yeah. And there's even more cookies in the kernel pool, a non-executable kernel pool. They greatly improved the randomization. With Ivy Bridge CPUs, which are the modern Intel ones, maybe even around for about 8 or 10 years now, these have a hardware random number generator, so you can get really random numbers. And I think Windows uses it. And this is an issue, of course. If you don't have a good random number generator, it's very hard to be sure if your random number generator is good. So they added a hardware one in the processor just to help with this sort of thing. Unfortunately, a lot of people refused to use it because they just assumed it had been backdoored because of the Snowden revelations. But there's never been proof it was backdoored. But of course, how do you audit the hardware? Unless you have, I guess, an electron microscope and you tear it apart, I don't know how you can really tell exactly what the hard trip is doing. Going to Redmond, yeah, that's right. It would be a road trip to Redmond, the Blue Hat. At least it would have used to be. These days, it's probably virtual. And this is the issue, of course. People freaked out because of Snowden and said RD-RAND might have been backdoored. So FreeBSD refused to use it. But of course, Microsoft did, because Microsoft is very much in bed with the government, very much cooperating. They would cheerfully use it even if they knew it was backdoored, probably, because they're selling their stuff to the government and the military, and they just want to conform to their standards. And so there's a bunch more new Windows Defend defenses, just a lot of them. For man-in-the-middle attacks, they have something called SMB signing and mutual authentication. To block bootkits, they got UEFI secure boot. So it validates the kernel on the way booting up like an iPhone does. So you can't have a kernel rootkit. And that's also down here. In rootkits, there's again trusted boot to make sure that nothing has been modified. One thing about these defenses is on machines with trusted boot and on iPhones, you can't replace it with Linux. It will fail that test because it tests to make sure that the kernel is actually signed by Microsoft or Apple. So you'd have to turn that defense off to put another operating system on your box. And here's a lot of things. Improvements in address-based layout randomization, protected processes, and many other defenses have been added in Windows 10. So Windows, is getting stronger and stronger all the time. Smart Screen, you've seen this. Smart Screen will detect that your browser is downloading something from from a site it doesn't like and block you from downloading it. And they moved most of the dangerous extensions from the browser. People used to have ActiveX and Browser Helper Objects and Flash, and they pretty much got rid of all that. All those things were serious security flaws. And they've got app container-based sandboxing to try to have defense in depth so that even if you exploit one browser process, it can't get out and take over the operating system easily. So, many good defenses. In OpenBSD and FreeBSD, there was an old thing called PHKeyMalloc, and now they've switched to Mmap, which randomly locates chunks of RAM and makes sure that no two chunks can ever be adjacent. So now, if you overflow out of a chunk, it won't be easy to hit another chunk. So that's one way. All right, so it's getting very difficult to exploit the heap, but sometimes there's something else stored after a heap chunk that's useful, like a function pointer. So that happened in one of the heap overflows you did here in the Easy project, where we put a pointer that was actually used for the instruction pointer right there next to it on the heap, so you could see it. And that's not very often the case, but when it is, of course, then it's easy to exploit. And then there's the structured exception handler. To protect this, it registers 0 before calling the handler. There was an old problem in, I think, XP, that the structured exception handler EBX always pointed to the instruction handler after it returned from there, so you could find it easily. Or somehow the EBX was useful, but they fixed that. You can't put it on the stack. And it has safe SEH that we talked about. This has an allow list of permitted exception handlers so that only those approved exception handlers can be used, so you cannot change the handler to point somewhere else, which is a good idea. This blocks trampoline attacks like what we used. But you have to recompile your code with safe SEH. to make this take effect. And there's EE-Reap that is your exploitation tools. This will find your trampoline code. Mona does the same thing. PDEST will freeze a process and hunt through it. SEH Inspector will check and see what defenses are turned on. So these are useful exploitation tools for the SEH. And that's it. Let's look at the last Kahoot, which is 14C. There we go. All right. All right. So how do you bypass ASLR by letting you specify where the code is? Return to gets does that. You type in data and you specify where you want it to go. So you don't have to hunt for it, you know where it's going. All right, which one places function pointers in a predictable location? That was Linuxgate, a table of pointers that's always in the same location. All right, which one might have been poisoned by the NSA? At least the BSD people think it has been. Yep, that's the hardware random number generator. All right, how many guesses will it take to find two independent random 8-bit values? $65,000, and each one is 256. To find two of them, you have to multiply 256 times 256, and that gives you 65,000 possible guesses, possible values. So it'll take about that many guesses. All right. All right, that's DDD. Good. Okay.